Hi, myself Dr. Priyodip Das, Research Associate Professor, Department of Chemistry, SRM Institute of Science and Technology. Today, we are going to discuss few important topics related to organic photochemistry. The topics covered today's lecture is the intramolecular and intermolecular hydrogen abstraction, Norrish Type II reaction, and Photocycloaddition of ketones with unsaturated compounds. Now, we are going to discuss about the first one, the intermolecular hydrogen abstraction, that is the gamma hydrogen abstraction. 1,3-N2 piastridic excited carbonyl compound having an accessible hydrogen atom in the gamma position, which can undergo a characteristic 1,5 hydrogen atoms transfer by an intermolecular cyclic process, with the formation of a ketyl like 1,4 diradical. As we seen in this example, this gamma hydrogen can be going to transfer towards the oxygen via a 6-membered cyclic transition state. So at first, in presence of light, it is going to the singlet excited state or triplet excited state. Then the cyclic transition state is produced. Finally, it is converted to this 1,4 diradical. So, depending on the conformation of the initially formed 1,4 diradical, two different pathways to stabilization are possible. What is the first one? If only the sp orbital of the radical center can overlap a cyclobutanol which is present in the product, and if the sp orbital of the radical center are parallel to the beta bond, they participate in the formation of two double bond, one in the enol and one in the alkene, a result of the cleavage of the beta bond. As we see, this diradical going for the two pathways. And if you look, this diradical, first of all, in the first pathway, this is the overlap of these two radical, and the cyclization takes place. It is produce a 4-member cyclic compound. And second, the beta bond is there, and there the sp hybridized orbital. So here the cleavage of the beta bond takes place and we produce this enol, and finally we are also getting this alkene molecule. And the second process of this reaction, that is the formation of the enol and this alkene, is known as the Norrish Type II process, which leads to the formation of these two products. This one is the alkene, another is the enol, which can be converted into the stable keto form as depend on the situation. Now, the quantum yield of the reaction is poor since the radiationless deactivation from the singlet excited state and triplet excited state towards the ground state and reversal of the hydrogen transfer, that is the opposite way. The reverse reaction of the hydrogen transfer can also compete with the reaction, proceeding to give the final product. The reversal process is confirmed by using the optically active ketone. Now here we can see the number one. This number one is an optically active ketone, and this optically active ketone, when undergoes racemization, then the racemization reaction confirms that the reaction intermediate 1,4 biradical, and this also confirms the back transfer of the hydrogen atom, that is the reversal process. If we look into that example clearly, we have seen here that this is the optically active center. In presence of light, the 1,4 biradical is produced, and this is the, then this can give a rotation around this reversal bond, and where you can see the C2H5 group which is above the plane, in this another one it is coming below the plane, and CH3 group is above the plane coming to the below the plane. So this is actually enantiomer type. And this, the back transfer of the hydrogen atom, that is the photodimerization, can be quenched by the addition of 1,3-cyclopentadiene, and this quenching experience confirmed by the formation of the triplet state. So that's why if you look into that procedure, we have seen the next example. In presence of light, that is happened from the excited triplet state from N to pi asterisk. This is converted this biradical, alkoxy biradical, and then this biradical go for a rotation around this carbon-carbon single bond to change the position of R2 and R3. Then the reversal of hydrogen process is happening. So again, this is produces a ketone, and this hydrogen from this position comes back to the gamma position. So these two, this ketone is actually a enantiomer of this number 1, and we are getting ABCD. What are the ABCD? We are getting, if this diradical go for a cyclization is happening here, we can see, and this is also produce enol, that is C, and this ketone can produce the first diradical, it is going to produce the C, and again it is produce the alkene, that is D. So the participation of a 1,4 diradical intermediate in the Norrish Type II reaction has been confirmed by trapping experiment and spectroscopic technique. So the formation of this 1,4 diradical has also been proven chemically, and this photoracemization of a ketone with a gamma chiral carbon atom and loss of chirality in the product was observed. Why the loss of chirality is happening? Because it produces the exact enantiomers, equivalent amount. That's why the optical activity is 0, and you can see that is the loss of chirality is there, and that prove that the single bond rotation and produce the ketone with exactly opposite chiral center. If this is the R, then this will become the S. Now the gamma hydrogen transferred to the oxygen atom has been shown to be intramolecular, and the transfer involved a 6-membered cyclic transition state. So the 5,5-di deuteriohexane 2-one, as shown in this example, on irradiation give 2 deuteriopropene and 1 deuterioacetone. The formation of these products confirms that the transfer of hydrogen takes place from only gamma carbon atom, and this process is intramolecular. So this is the example which can confirm that this is the system is produced alkene, and this is the ketone. Initially the enol form is produced, which can get automerized to ketone, which can confirm the intramolecular hydrogen transfer from the gamma carbon atom. So when a molecule has 2 gamma carbon atom, when a molecule has 2 gamma carbon atom and both having hydrogen, transfer of the hydrogen in the Norrish type II process is marked by preference of cleavage of the weaker carbon hydrogen bond, as shown in this case to ketone 2. So here we can see this is the one of the gamma carbon atom with CH3, and this is the one of the gamma carbon atom. So this is actually a weaker, and if the hydrogen moves from there, it will produce the most stable radical compared to that primary radical CH2. That's why always the gamma carbon prefer from that weaker CH bond, where we can get the most stabilized radical also. So this intramolecular hydrogen abstraction is not possible if the gamma carbon has no hydrogen atom. Now the rate of the radical recombination to give the cyclobutanols compared to this alpha beta bond cleavage is often dependent on the alpha substitution. As for example, here we see that this is the alpha carbon, this is the beta, this is the gamma carbon, and the alpha carbon having a substituent R1 and R2. In presence of light, it can raise this ketone molecule and this alkene, and another path it can give is this cyclobutanol derivative. Now, if the R1 equal to R2 equal to H, then cyclization is 10%. If R1 equal to H and R2 equal to methyl group, then the rate of cyclization is 29%. And when R1 and R2 both are methyl group, then the rate of cyclization is 89%. So what we observe or what we conclude from that, when the size of the substituent at the alpha carbon atom corresponding to the carbonyl group is increased, we can see the rate of cyclization is increased. That is, the path 1 is followed to produce the cyclobutanol derivative. On the other hand, substituent at beta position favors Norrish type II reaction. Thus, this ketone 3 mainly give Norrish Type II reaction, that is elimination reaction. In the other words, if the 1,4 diradical is stable, then this favor cyclization reaction. And if 1,4 diradical is unstable, then this will be favor the Norrish Type II reaction. So here it is clear, if this 1,4 diradical is unstable, that's why, because CH2 radical is there, primary radical, this is unstable, it preferred the Norrish II reaction, that is the cleavage to produce the enol and the alkene. But if this one is stable radical, then it will prefer the cyclization reaction to produce the cyclobutanol derivative. Now let us complete one example. So now here, this is the molecule ketone and we give the H nu cyclohexene. So what will be the solution? That is the hints that the compound has the hydrogen and gamma carbon. So that is the necessary condition we tell in the last slide. So which is an allylic carbon. That's why if allylic radical is very stable, hence the 1,4 biradical has a allylic character, and we know the allylic radical is stable. That's why it will go for the cyclization reaction. And we can see this is the final product, the production of the 4-member cyclic system. Let's see the hydrogen atom abstraction from other sides, that is except gamma position. So while the normal reaction of Norrish Type II process involve a 6-member cyclic transition state that we usually see in the previous many examples. So what is the alternative reaction path that is fairly common for other molecule? In these cases, either a larger or small transition state provide diradicals. So which cannot fragment, but the cyclization can happen. So the alternative routes are possible when this gamma carbon has no hydrogen or biradical is stabilized by a heteroatom. Now let us consider the first example. Now if we consider the first example, we can see here the biradical is produced after the extraction from this alpha and beta position. So this beta hydrogen going to abstract by the oxygen to produce this diradical, and this radical, the CH radical, is stabilized by the heteroatom. So its leads go for the cyclization reaction to produce this cyclopropanol derivative. Now let us consider the second example. So what is the second example? We can see that this diketone compound has transferred this hydrogen from the beta position towards the oxygen, and this one is again stabilized by this ketone group through the resonance. So this radical is also stable and leads to go for the cyclization reaction to provide this cyclopropanol derivative attached with this carbonyl molecule. So both these cases we observe that the radical produced is either stabilized by the heteroatom or this carbonyl group leads go for the cyclization reaction to get the final cyclopropanol derivative product. Now we have another few example, that is from delta or epsilon hydrogen abstraction. So here we can see there are other systems where the hydrogen abstraction through a 6-membered cyclic transition state is not possible because there is no suitable place hydrogen atom. As for example, the 1,8-benzyl naphthyl phenyl ketone is such a compound, this second one. And here you can see after treatment with the H nu at 366 nanometer, it can produce this molecule where the cyclization happen and a new 5-membered ring is produced. And in this case, the first example, if we have this H nu in presence of light, there also cyclization happen and produce two different 6-membered ring with the OH substituent. So this hydrogen atom abstraction can be possible from, you can see this, if we consider this is the alpha 1 position, the 1, 2, 3, 4, 5, 6. So alpha, beta, gamma, delta, epsilon position. So from long distance hydrogen, the cyclization is also preferred and give the cyclization product. Now if we consider the hydrogen atom abstraction from distant side, in the photolysis of the alkyl ester of benzophenone 4-carboxylic acid and shown in this example, the planar transition state is possible only for greater than equal to 10. So which leads to the formation of a 118 biradical whose recombination produce the paracyclophane. If you see this one, so this is the 1n number of diradical, and finally this cyclization reaction happen that can produce the paracyclophane derivative. And more importantly, this intramolecular gamma hydrogen abstraction by an excited state carbonyl oxygen is approximately 20 times faster than this delta and epsilon hydrogen abstraction. So nevertheless, the tendency of an half occupied n orbital of the carbonyl oxygen to abstract a hydrogen apart from other position is considerable. So what is the necessary condition? The necessary condition is the planarity of the transition state. So an important example is shown in all this molecule where the planarity is obtained. So in this case, the intramolecular hydrogen abstraction takes place from C6 position also when it confirms the planarity in the transition state. So now we are going to discuss about the formation of photoenols or photoenolization reaction. The formation of photoenols arises by the Norrish Type II process in ortho-substituted aryl ketone and are produced by the following mechanism. Here we can see example of the ortho-substituted aryl ketone. In presence of light, it is going to convert it into singlet excited state. Followed by intra-system crossing, it is going to convert into triplet excited state. And where both in this diradical, both the electron have the similar spin. Both the electron have similar spin. That's why the spin multiplicity 2s plus 1 equal to 3. Followed by the spin inversion, it can produce this singlet diradical. If we see this one have a two opposite spin. Now this going for a product. One is the Z isomer, another is the E isomer. The photoenolization can be quenched by the molecular oxygen. So this is the indirect proof of this mechanism. And this confirmed by the formation of the triplet biradical. This is the formation of this triplet biradical. And the product of the reaction behave as a diene. So the E and Z isomer can behave as a diene, and it can be react with a dienophile to give the Diels-Alder product. So this is the example. Here we can see this Z isomer can react with the dienophile to produce the Diels-Alder product. Now this is another important class of reaction, that is the Photocycloaddition reaction or Paternò reaction. So this Photocycloaddition reaction is one of the first Photocycloaddition reaction to be studied. Was the formation of oxetanes from addition of carbonyl compounds to alkene. So this reaction is very well known to the Paternò reaction. For example, here we can see the benzophenone with isobutene. So this benzophenone with isobutene can react to gives a high yield of oxetane, and the yield of this product is 90%. So this Paternò reaction can be studied under two categories, and these categories depend on the nature of the alkene. So now first mechanism we are going to discuss, the addition to electron rich alkenes. So mechanistic studies have shown that the reaction pathways varies according to the type of carbonyl compound and alkene used in this Paternò reaction. So addition of simple aliphatic or aromatic ketones to electron-rich alkene involves the attack on the ground state alkene by the N2 pi asterisk triplet state of the carbonyl compound in a non-concerted pattern, giving rise to all possible isomer of the oxygen. And the reaction is non-concerted because the reactive excited state is a triplet state, not the singlet state. And the initial adduct of this reaction is a triplet 1,4 diradical, which must undergo spin inversion before the product formation is complete. And the stereospecificity of this reaction is lost if the intermediate 1,4 biradical undergo bond rotation faster than the ring closure. Then we can lose the complete stereospecificity of this reaction. Now see, here the addition of electron-rich alkene towards the aryl ketone. Initially, in presence of light, it is converted to S1, singlet excited state. Then intra-system crossing going to convert into the triplet excited state. And this is the excited state triplet. react with this alkene molecule, electron-rich alkene molecule, and produces this triplet derivative, and then it is going to intra-system causing, then the spin inversion happen and finally give this 10% oxetane derivative. And this is the another triplet one. Here this is going for another spin inversion process and followed by the cyclization to give the 90% yield. So basically the two important rules for the successful synthesis of oxygens have been put forward. What is the rule? The rule is one carbonyl compound with a low-lying N2 pi asterisk state will form oxygens. And what is the second rule? The energy of the carbonyl excited state must be less than that of the alkene to prevent the energy transfer from the carbonyl excited state to the alkene. So as far as the addition of the aromatic carbonyl compound is concerned, only the triplet excited state is reactive because intersystem crossing is very efficient in case of aromatic ketone, and consequently a triplet biradical intermediate is produced. And the reaction of the alkyl ketone can be complicated by the less efficient intersystem crossing, thus permitting reaction of both the singlet and triplet state. So both the singlet and triplet state show equal reactivity for this reaction in the case of alkyl ketone if we use, and the singlet state reaction obtained at very high concentration of the alkene. On the other hand, triplet state reaction obtained at very low concentration of the alkene. Now, if we consider this addition towards the electron deficient alkene, then the Photocycloaddition of the aliphatic ketones to the electron deficient alkene, particularly dicyanoethene, involve the addition of singlet state N2 pi asterisks excited ketone to ground state alkene, and the reaction is highly stereospecific and the stereochemistry of the alkene is retained in the product oxetane. So if we see this example, we can see the course of the photocycloaddition of electron deficient alkene to ketone follows certain rules, while the oxetane are formed only from singlet N2 pi asterisk excited state S1 and the triplet excited state T1 N2 pi asterisk state stereospecifically sensitize the cis-trans isomerization of the electron deficient alkene and doesn't lead to oxytanes. So here you can see the clear example here. So if it is from giving for the light of 330 nanometer, that is also electron rich, that's a electron deficient alkene, a cis electron deficient alkene, and this is a trans electron deficient alkene. And when it reacts with the same ketone, we can give this oxetane derivative. But when it comes to the triplet excited state N2 pi asterisks, then this reaction is not going to happen. Then isomerization of the cis trans isomer happening of this alkene. So you can see this is an cis alkene converted to the trans alkene, and here it is a trans alkene going to convert it into the cis alkene. The stereospecificity of the oxetane formation with electron deficient alkene can be explained as follows by this example. So here you can see it is suggested that in case of the electron deficient alkene, oxetane formation takes place by the formation of the exciplex, and the exciplex formation takes place between the singlet excited state of the ketone and ground state of the alkene. So exciplex is stabilized by charge transfer as well as energy transfer between the constituent molecule. So here you can see the formation of the exciplex of a carbonyl excited state and an olefin ground state. And number B is the charge transfer interaction in the formation of carbonyl olefin exciplex. So that is the N2 pi asterisks, and this exciplex formation, that is the exciplex formation, and we can give the final oxetane derivative. So this exciplex is stabilized by the charge transfer as well as the energy transfer between these constituent molecules.